So we will continue with our course, and last thing we did was to study the behavior of this synchronous generator connected to an infinite path, but now with a short circuit. The short circuit occur at the terminal of the synchronous generator. So when the short circuit happened, then the electrical power instantaneously was set to zero. Angle delta cannot change because it's a state variable related to the kinetic energy, the motion of the generator, so it cannot change. But if the short circuit remain as the electrical power is zero, then the generator will be accelerated and the angle and the speed will start increasing. And this will increase until somehow this fault is removed from the system. So in this case, we consider the self-clearance, so that somehow the short circuit is not there anymore. And when that happened, the electrical power instantaneously changed to whatever electrical power we had before, but now we have a larger angle. Therefore, the electrical power became instantaneously way much larger than the mechanical power. Now, as the accelerating power is Pm minus Pe, the accelerating power is negative, and this will make the machine stop this increase in the angle. Because of the inertia, the angle will continue increasing, but because of this negative acceleration, at some point that angle will stop increasing and reach a maximum value. As we still have a negative acceleration, then the angle will start decreasing, moving along the electrical power curve. And because of the inertia, probably this will continue down, but when the angle goes down, again, the electrical power will become less than the mechanical power, and you will have a positive acceleration. That positive acceleration should stop the decrease of the angle at some point, reach a minimum angle, and then start speeding up again. If the system has damping, then this will oscillate until the machine converges to that equilibrium point. That's what we did. We got a code in MATLAB, and we got some result with different clearing time. So if the clearing time is 0.3 seconds, this is the plot of the angle in time and the plot of the speed in time for that clearing time. So here is the phase plane, and this is the trajectory of the system. We start from the equilibrium point right here. You have the short circuit. The short circuit is clear, and because the system is stable, get trapped by the stable focus and converge again to the same equilibrium point. If we increase the clearing time to 0.45 seconds, then we still have a stability. The excursion in the speed and angle is much larger because the short circuit, as you can see here, remain longer. So we surpass this point, and at this point, the fault is clear. We're still in time to stop this short circuit and acceleration of the machine, and the machine again gets trapped by the stable focus and become stable. But if we do it too late and just a little bit more, the clearing time here is 0.48 seconds, then we cannot save the machine, and the machine, after we cross this eigenvector related to the stable eigenvalue of this saddle node, when we cross that line, then the system just diverge. So we also discussed what happened after a while, and after a while, it seemed that the machine converged. It seemed that this oscillation is getting damped out, and at some point, maybe the speed will converge. The angle now is very large for this case. I don't know how large it is, close to 90, maybe 90 radians, and we talk about this. So, David, right?
Davis.
Davis? That's your last name?
Yeah, Ryan Davis.
Ryan. I got confused. So we have three David. David, no, two David and one Davis.
Yep.
So Ryan.
Yes.
So you mentioned, Ryan, that it was kind of the pendulum, right? And in the pendulum can go and take a whole lot and everything seems fine. And then at some point, the angle can go like plus 2 pi, 4 pi, 6 pi, and everything seems fine, and there is no problem. And the pendulum at some point, if we have some damping, will converge to the stable focus, which is at the bottom, right? And it seems that that's the case. And mathematically speaking, you're right. This work, you know. But in a practical setting, when you have equipment and you have other thing that you need to look at, voltage and current, that might not be allowed. And that's what we have here, because as the angle increase, then we need to calculate what is the current and what is the power. And I asked you to do that exercise. I don't know if you had time to do it, but if you calculate that, did anyone do it?
I'm real busy with power electronics.
Really?
I looked at the
Current?
for this problem, but I didn't calculate it.
Yeah. Well, in the same code, we can do it, and we can do it right now. We can calculate that current, and we can plot the magnitude of that current. We will see that it's very large. It's like comparable to the short circuit current. So that situation, if that situation remains for 7 seconds, that's not practical. These large current during the short circuit, they're typically clear after a few cycles of the signal, less than 100 milliseconds, you know, in that range. Because if we let the current remain longer in the system, that's dangerous. Some equipment can get burned, you know, because of those high currents. So that's the issue with this. We have this other component. We need to look at the electrical grid and the constraint that we have there. If this is not, we don't care about that current, then it's pretty similar to the pendulum. You know, it can converge again to, after a while, to another equilibrium point. Okay, we're going to move further and consider another example. Then hopefully this Friday, we're going to talk about a classical concept that we use to determine whether the system will be stable in the first swing or not. You see here, when you have the short circuit, and then the angle reach a maximum value, like in this case, then the system gets trapped by the stable focus and become stable. We call this the short circuit and this maximum angle the first swing of the oscillation. If everything is fine then there, we can say, well, the machine survived. It's going to be stable. And we call that the rotor angle stability. We just focus on this part. So we will discuss that criterion that can help us to determine whether the machine will be stable or not. And we're going to be done with this first part. What after spring break, what we're going to do, we're going to add a more detailed model, because we have been using the classical model. We will consider other practical thing in the machine, and then we will move to consider multiple machines and how we can simulate that situation. And after that, we should be fine to start discussing voltage control, frequency control, power system stabilizer, and then we will discuss wind turbines. Yeah. That's what is coming. For this part, as I said, we have the code, and this is in Canvas, so you can download it and play with it. So what I'm going to do here, we're going to simulate. What was the clearing time? 0.48, I think. 0.48 second. And that's the case. So in the here we have in the workspace, we have here the size. What is this? The size of the matrix with data. The first column corresponds to the angle second column correspond to the speed. So I will store the first column of this in the variable delta. So the current then, the current in the system will be it's going to be E times exponential of J delta minus the voltage at the infinite bus divided by the total reactance. The total reactance in this case is here we have the short circuit, and then when we clear the fault, then the total reactance will be XS plus XL. We put it there. Oops, on the plot, this one. XS plus XL. So here we have the current. But the current we are calculating is after we clear the fault. So we need to determine when the at what point in this vector we have the clearing time. So we can try here something. Well, the clearing time is much less, so it's hard to find it. So we can use the function find here, find t that is less or equal to 0.48. So 42. So time data 42 will give us the clearing time. So what we're going to do here, we're going to create, we're going to create another figure, figure 10, and we're going to plot the time, but we're going to do it from 42 to the last value. And we're going to plot delta. And again, from 42 to the last value. And not delta, we're going to plot the current. But for the current also, we're going to get the absolute value of the current. So that's how we do it. And we didn't do anything. What happened to the current here? Did we calculate the current? I thought that we did it here.
Do you have access to Excel?
Let's do it again. How much is delta? Delta, consider all the values we have. Yep. And then we have E. Yes, we have B, XS, and XL. And then we calculate the current in that fashion. So E exponential of J delta minus B, close parentheses, divided by divided by J times XS plus XL. So that's the current. And the current should be a complex quantity. Yes, we can see what we have. Yeah, it's a complex quantity. And if we get absolute value of the current, then you have that. So why we're not getting the plot? Oh, my fault. Yeah, that's my fault. From 42 to N, that's what we need to do. There it is. Yeah, finally. So what do we have here, Ryan? Is the current. It's the current in per unit, right? So the current in per unit, and this is after we clear the fault. So what happened? It increased even more. We reached to this value per unit, but then because the angle is increasing, because we were not trapped by the stable focus, but kept going, 2 pi, 4 pi, and continue, then the magnitude of the current will do this. So in any system, due to practical reason, we're not going to let this current be that high for so long. So this is a situation we will never allow. A protection scheme typically will try to clear a fault in a matter of a few cycles, like 5 cycles maybe of the signal. We're talking something less than 100 milliseconds. Okay, so the same thing you can do with electrical power. Do the electrical power and see what you get. What did I say last time about electrical power? What might be something odd with electrical power in the machine if we let this happen?
Oh, it's acting as a motor.
A motor at some point. So let's check that if that is the case. Okay, so we're going to consider another situation because the disturbance that we consider is a 3-phase short circuit at the terminal. When we have this, the electrical power coming out of the generator is 0. But what about if the fault happened in some other part of the system? And we have another example here to consider that case. This is the same system, but the line now you have 2 circuits. These are like these towers that you have 3 phases on one side and 3 phases on the other one. So you increase the power transmission to the transmission line. The reactance before for our line, you remember, was 0.3. Now we have 2 circuits, but each one of them is 0.6 intentionally. Why? Because the 2 in parallel will have a reactance, equivalent reactance of 0.3. So together, this is exactly the same than we had before, right? Are you with me? Are you with me? Now, in this situation, then we can calculate the equilibrium point. Everything is fine. We are sending this power to the infinite bus, and the equilibrium point should be exactly the same angle delta for this machine, which was 0.24, I think, radian, something like that. The equivalent reactance XL over 2 is 0.3, which is the same value we considered before for the line. Yeah. So that is the case for the equilibrium point. That's the characteristic of the electrical power. We calculate the equilibrium point and we get delta 0. So this is going to be called the electrical power before the fault. And I put it in blue. But we're going to consider a short circuit. The short circuit can be applied here to the bus. That can be a possibility. But the short circuit can be on the line. And it can be on the line very close to that bus. We're talking about feet away from that bus. From the electrical point of view, it's like the short circuit happened at the bus, but physically, the short circuit is at the line. So if the short circuit happened at the line, we have an option now. What is the option? We can use the breaker to isolate the fault if the fault is not self-clear. But when you isolate the fault and you open this breaker after a short period of time, then you are modifying the grid. Now the line is not going to have an equivalent reactance of 0.3 as we had it before, but now you're sending power just through one line, and that will lead to a higher reactance. So that's a big difference. For simplification here, we're going to assume that the fault happened right in the middle of the line. Okay, a short circuit. We're going to consider a clearing time. We will play with this later. But between 0 and the clearing time, you will have that situation with a 3-phase short circuit in the middle of the second circuit of this line. If that is the case, the impedance that you have from bus 1 to the middle of the line is 0.3 per unit. So JXL over 2, that's what you have. And is that impedance between the phase and the neutral. Yeah. So from here to here, again, you have half of the impedance, which is here. And that is the impedance between bus 2 to the neutral, right there. So before these 2 points were connected, and you have a second react impedance here that was in parallel to this, but because of the short circuit now, that point in the middle is sent to the neutral. The other line remained there, but as we discussed, this has a impedance J 0.6, which is large. Now, during the short circuit, that is the situation. What can you tell me? Is this any different to what we had before?
Yeah, during the short circuit, we won't be able to transfer as much power, electrical power.
We're going to be able to transfer electrical power?
You'll still be able to transfer. It won't go to zero, but
It won't go to
It
zero.
won't be as much as it was. The blue curve will drop.
So that's the first observation. Now, how much is electrical power? By inspecting the circuit, do you know how much it is? What do we need to do? Well, this part is bothersome. Why? Because you have this node in between. So what we typically do in these cases, we want to convert this, make a transformation of impedances to take this to something that we know better. If we need to calculate the current over this branch, what do we need? When you have the voltage on this side, then we need to have the voltage on this side. That voltage there, we can calculate it, but we don't know it yet. So the current will be the voltage here minus the voltage at this node divided by the impedance. That will be the current. But we don't have that voltage. So what we're going to do, we're going to make a transformation. So that's the situation during the short circuit, but we're going to transform it. If we call these node A, B, and C, then you can see that these three impedances are in a star. So what we're going to do is to make a star delta conversion. So we're going to call, instead of using these three impedances, we will use these three impedances that are going to be connected in delta. Now we need to remember what is the conversion, but I have it right here. So the impedance CAB is going to be the impedance CA, which is this part of the star, plus CB, this part of the star, divided by the impedance, this one plus this one, plus the multiplication of this and this divided by the impedance ZC. And that's the equation right there. CA plus CB, CA multiplied by CB divided by ZC. If we do that, we put the numbers that we have. This is 0.6, this is 0.3, this is 0.2. We plug it, we get that for the impedance between these 2 points. As the result is purely imaginary, we can call the imaginary part of this XAB. The same thing, similar thing for the other impedance. This is going to be ZB plus ZC plus the multiplication of these two impedances divided by this one. We plug the numbers, we get this, and finally this impedance, there is equation. Now that we made this calculation and we know these impedances, we are going to replace this star here by this delta. This point C is nothing else than the neutral. So we will have that description now. We have converted the impedance. Now we like this. And what we are looking for, we're looking for the electrical power that will come out of this generator. And to calculate electrical power, we need, as we know the voltage, this is fixed. This is the state variable. We know this. What we need is to determine the current. So that current will be by Kirchhoff current law, this current AB plus the current AC. With this configuration, it's easy to calculate this because you know the voltage here given by this, and you know the voltage here, which is fixed, is given by the infinite bus. So with those two voltages, you get the difference divided by the impedance, and then you get the current through that impedance. For this one, also it's easy because the voltage here is the voltage from your generator. You divide that voltage by this impedance, then you get that current. So this delta is star delta conversion is useful. We can calculate this current easily. We replace that here, and then we can factorize by E. If we do that, you get this expression. We can take this term that depends on voltage B from the infinite bus and put it right there. That's the current. Now, we need to calculate the electrical power is E times the current conjugate, this expression conjugate. So you have E, and we will multiply by the first term first. So this is going to be conjugate, E conjugate. And these impedances are going to be conjugate as well. That's the first term. Second term, B is real, remain the same, and these become negative right there. Well, we do the multiplication of 1 over negative j is just j. We put j there. E times E conjugate is just the magnitude of that phasor square, E squared. And this term is just there because we factorize it by j. The second term, this is going to be 1 over negative j is just j. And then you have E times B divided by that reactance. And the angle of delta will show up there. The angle of this is 0. Now we get the real part of this. This is purely imaginary. The real part of that is 0. And then here, because exponential of j delta has 2 components, it's cosine of delta plus j sine of delta. So the cosine of delta will lead to an imaginary number. That doesn't work. We pick the j sine of delta. J squared, negative j squared, just plus 1. And then you have EB over XAB sine of delta. So that's the expression for the electrical power during the short circuit. We replace the values we have, and that is the expression for the electrical power. So as David said, the main difference is now the electrical power during the short circuit is not 0, but it's something, and that's the value. So now that we obtain this electrical power, we have this description. During the fault, now we don't have an electrical power that is 0, but has this function. Finally, because this fault, one option is that we have a fault that is self-clear. Now we're going to isolate the fault by opening the contact, the breaker at the end of this circuit. So if we open the breaker, then this is de-energized. This is removed from the system. Therefore, there is no short circuit anymore. By doing that, now the line just behave like the first circuit. So the total impedance is going to be JXL. This is 0.6. This is not as the previous case where the impedance was J 0.3. This is twice that value, but still it's better than not having an energized synchronous machine. So in that case, what is going to be the electrical power? Well, we don't have to do much here. We remember what was the electrical power before the fault. All that we need to do is to get the magnitude of E, magnitude of this source, divided by the total reactance, which is XS plus XL, sine of delta. The angle of this infinite bus is 0, so delta is the angle of the machine. So after the fall, we will have this situation. We plug the numbers, and this is the maximum power. So before the fault, we have 2.1. After the fall, we have 1.31, which is not great, but we still can transmit this power to the infinite. So one thing that will happen here, if everything is fine and the machine survives, it's still stable, we will move from that equilibrium point to this equilibrium point. So the angle delta will increase a little bit because we will be operating just with one circuit in the transmission line. What is the situation now? So before the fall, the system was fine, stable. We have an equilibrium point with an angle delta 0. The speed is 1 per unit, and we have a short circuit. The electrical power immediately changed from PE to PEV. So at that time, 0, the electrical power will immediately change from this point to this point instantaneously. Delta cannot change because it's a state variable. And because electrical power now is less than the mechanical power, the machine will accelerate. Angle and speed will start increasing. So the angle will move along the curve of PEV, the electrical power during the short circuit. At some point, we will clear this fault because the protection scheme will respond, will open the breakers on the extreme of the line, and the fault will be removed. At that point, the power immediately change to the power after the fault. So this is going to be an instantaneous change in the electrical power. Now, because the speed and angle was increasing and you have some inertia, the machine will continue to increase those variables, but now we have a negative acceleration. So that increase in the angle at some point will be a stop. And let's assume that that is the case, and that is the maximum angle that this machine will reach. As the acceleration is still negative, that angle will start be reducing and will move along the green curve. And at some point, we will reach that point where we should have the equilibrium, but because of the inertia, the speed and the angle were reducing, we will pass this point, and then you will have again a positive acceleration. At some point, that decrease in the angle will be stopped because of the positive acceleration, and we start moving up again, and the machine will oscillate until we reach the final equilibrium point that will be given by the intersection of this green curve and the red curve. So that's the situation. We can use the same code we had before, but we need to do some tweaking. We will have the definition of data. We need to calculate the equilibrium point using the electrical power before the fault. We will assume the short circuit is at time 0. We will assume a clearing time. We will define the parameters of the solver, and we're going to be ready to invoke the solver for the first time, and that is going to be during the short circuit. So the time will be from 0 to the clearing time. We invoke the solver with the variables t1 and x1, and here we need to make sure that this function corresponds to the equation during the short circuit. The main difference now with what we had before is that the electrical power is not 0, but is that sinusoidal function we obtain. When we have the solution here, we need to get the state variable after the fault, and we will use that as initial condition for the next simulation we will run, which is after we clear the fault. We invoke the function again. We're going to store the variables as t2 and x2, and the function will be f with a new initial condition. The last values we have for the state variables before we clear the fault. F now we will need to have the equation when the fault is clear. So the electrical power here will need to be the one after the fault. When we get the solution, we will concatenate the result for time and the state variables, and you should not forget that the function needs to be defined as a sub-function at the bottom of the code or a separate M file. Why am I repeating this? Because we need to simulate at some point multiple generators. And things will be a little bit different, but this structure will be exactly the same. Okay, so I don't have any plot here in the PDF. How we're doing with time? We have like 12 minutes. So what we're going to do, here's the equation. So we have before electrical power during the fall and electrical power after the fall. The first one is EBXS plus XL over 2 sine of delta. The second one is XEB over XAB sine of delta. And the last one is EBXS plus XL sine of delta. And the value for this is 13125. For this one is 0875. And this one is 2.1 sine of delta. So those are the equations. And let's work on the code now. I'm going to save this with a different name. This is going to be example D. The data is a little bit different, so we will change that. Everything is the same, but XL is 0.6 now. Zero 0.6. So we have a Pmax in the data. We need to change this as well because this is that divided by 2. So that's the new Pmax. So PM is given in the data is 0.5 per unit divided by Pmax. That will give us delta 0. We will have the input function here. We will have the clearing time. We define the time, invoke the solver with this set of equation. So we need to check the set of equation we have during the short circuit. Here's the set of equation for the short circuit. So what is different here? The electrical power is not 0. So here we can calculate the electrical power, PE. We can put the name during the short circuit. And that's going to be given but the equation that we have in the whiteboard. Yeah. So that equation is going to be, we have the data EB over XAB. We can put the equation there. What about if we put directly the value we obtained, 0.75? But in a general system, probably would be better that we calculate there how much is XAB. So that's electrical power during the short circuit. And that's what we're going to put right there. So that's the new equation during the short circuit. We go back to the main code here. And after this, we will have the solution for time and the state variables during the short circuit. After we clear the fault, we use as initial value the last value we have for the state variable during the short circuit, which is line 17. We define the new time. We're simulating for 10 seconds. And we invoke again the set of equation after the fault. Now, F need to have the new electrical power because we have removed one of the circuit in the transmission line, which is this function. So again here, we need to define the electrical power, PE, after the fault. And then we can put the equation here, which is going to be EB sine of delta and divided by XS plus XL. And that equation need to go right here. It's not the power we had before the fault, but it's a new equation for the power. So that's different. When we are done with that part of the code, then we should have a solution for the state variable after the fault is clear, which is T2, X2. We concatenate the result, and then we do the plotting. So what we had before is this. We try 0.3 seconds. Everything seems fine. We try 0.5 seconds. The system is still stable, but it's getting very close to that eigenvector of the saddle node point. And at 0.48 seconds, the system just becomes unstable. So let's try that time and see if there is any difference. 0.48. What do you expect in this case?
We can have a longer clearing time since electrical power can still be.
What happens when we have more electrical power?
Then the machine acceleration won't be as drastic.
It will not be as drastic. And what happens with the angle and the speed? They will not increase as much. And therefore, we're not going to get that close to the saddle node. And the short circuit might remain a little bit longer. So let's see if that is the case. That's the situation. So you can see that we're far away, and just having, instead of one line with one circuit, as we saw, it's not that as great as having two circuits in that line. Having two circuits in the transmission line will improve the operation of the system, will increase the stability of the system as we have here. So we can play with this and see if there is any difference, if this time is a little bit longer, and let's say 0.6, and it's still robust. So if you're the operator in the power system, what you are going to be your solution for stability? One solution, well, we need to do what? In general, I'm thinking about the power grid. What we're going to do if we need to improve the stability of the system based on this exercise.
If there's multiple paths.
Multiple paths. We need to make the grid stronger, right? By adding new transmission line in the system will improve the stability of the system and will leave a better margin for this situation. If you have short circuit, then the system will be robust and can withstand short circuit better than not having a grid as strong. So I remember in the past you asked me about why we have the system is more prone to instabilities these days than it was 40 years ago. And one of the reasons that we discussed at that time is that before almost everywhere in this world, we have a system that were vertically integrated. There was no market involved. Who operated the system? It's one entity, yeah, that depended on the government that was there in that system. So generation, transmission, and distribution belong to the same company. And typically, the grid was well planned because the goal was only one: make sure that the system operate well, right? So at that time, you have good transmission system, multiple paths, and the system was very strong. But then at some point we realized, well, it's very costly. Is there anything we can do to improve this? And then we add the deregulation. Now the whole grid, generation, transmission, and distribution were not just operated as a one company controlling everything, but we add deregulation. We led the generation system to other companies to compete among them and compete to who provides better prices for electricity, and we deregulated. And then the distribution system, because of the nature of the distribution system, we cannot let competition there because of the physical limitation of lines in a city. Then we have a concession. We have a company, serving a given area. In the transmission sector, the same idea. We have a company that is in charge to operate the transmission system, but there is no motivation for expanding that as we had before. So with that new structure, the system started evolving. You started having more competition of the generation system, more potential for generating, but we did not have the same drivers of the transmission system. So we have more demand because population grows and the acquisition of new components for customers, the demand start increasing, generation start increasing, but the transmission remain almost the same with minimum changes. With that, then the system started becoming closer and closer and diminishing the margin of the stability of the system. Yeah, and that has to do with this concept. If we have a better, stronger grid, then the system will have a larger margin for stability. So we have just 1-2 minutes. We can leave it until here. What is coming on Friday? On Friday, we're going to close this chapter. It's the last thing we're going to discuss with one machine. This is called the equal area criterion. We don't know yet what is that, but we will discuss. And this was used before when all times when computers were not that massively used. So the engineer need to have some estimation whether the machine was going to be operating well or not. So we will discuss this next Friday and wrap up this part. And after a spring break, we should be able to start adding more complexity to our model. We're going to add a better model for the synchronous generator and start simulating multiple machines. Yeah. Thank you, guys.